Yes.
Good morning. Today we're going to talk about Newton's first law of motion. As you can see on my lesson plan here, the learning target for today is that you can explain Newton's first law of motion as well as the law of inertia and give examples. Let's start with the agenda. The first item on the agenda is the presentation, which you can click and access at any point in this lesson if you want to follow with me. However, I request you to just pay attention to what I'm saying and then be ready to ask questions if you have any. So without further ado, let's go to the presentation and let's start right from there. So the topic for today is, as we said, Newton's first law. Our learning targets specifically are to state and explain Newton's first law of motion, state and explain the law of inertia, give examples of inertia of rest, and give examples of inertia of motion. Let's start with a couple of videos to help us start thinking about Newton's first law and inertia of rest. So in this particular video that I'm going to play for you, there is a block of dry ice, which is solidified carbon dioxide, that's placed on a table. Now, when I play the video for a few moments, you'll see that the gentleman gave the block a gentle push and it slid on its own, as you can see there. Now, this behavior is rather unusual, right? When you compare it with the normal day-to-day behavior of objects. You see he's giving it a gentle push and it just seems to want to go on without stopping. Now, you might even wonder, like, what's all that smoke coming out from under the dry ice? Well, that's just solidified carbon dioxide that's vaporizing, right, and becoming carbon dioxide gas. And because that there's a layer of gas between the block and the table, there is a frictionless surface on which it can slide. And therefore, it's sliding basically on a surface that doesn't present any opposition to its motion. But before we talk about that specifically, let's look at another example. This is a very interesting and entertaining video, so watch and enjoy. David Jin's magic.
Again, welcome to the amazing, astounding, phenomenal tablecloth stunt in which you pull the cloth out from under the dishes, hopefully without breaking any. Now, I like to do this for real, not for comedy, so I use real china plates, the kind that if you drop them on the floor, they break. I've got bowls, plates, cups, and saucers. Would you like a cup of coffee? Oh, well, maybe not. There's one right there. Here, let's put this here. And on the count of three, I'm going to give that table a jerk, that cloth a jerk, and pull it out from under the dishes. Here we go. Wait a minute. You know what? We ought to have some music. How about some royalty-free custom music by my friends Leslie and Arthur Stead up in Massachusetts? This is really rockin' stuff. In fact, this cut is called Rockin' Rabbit. Play the music. Here we go. All right. Okay. On the count of three. 1, 2. Wait. Stop the music. Stop the music. You know what? Let's make this special. Let's have a special guest in this spot, and that guest is my rabbit, Harry the Magic Rabbit. Come on, Harry. Here you go. Look at him. Look at that white fur coat. Look at the little bunny ears. And he got red eyes because he drinks too much cherry Coke. What'd you expect? He's from Atlanta, Georgia. Now, Harry always likes to be in the center of the show, so I think I'll let him be in the center of the show. How about right in the center of that plate right here? At least he's not rabbit stew for lunch. Okay, play the music. I'm doing it this time. Are you ready, Harry? On the count of three. 1, 2, 3, now! My goodness, it worked! Harry, it's magic!
Okay, so wasn't that really entertaining? I've played this video several times over many years and it never fails to entertain me. What a wonderful illustration. But what is this all about, right? So let's come back to the presentation and let's think about
We have
both
this
these
entire
things,
misunderstanding of what Darwin really
right?
meant when he said
So
survival of the fittest.
I'm just going to close the videos because they're playing automatically, right? So what's this all about, right? So a person called Newton, Isaac Newton, whom you've probably heard about, thought about this. And he wondered why an object like dry ice with no friction would just keep going. He also wondered why, say, cutlery plates on a table would remain still if you yanked the tablecloth out fast enough, right? And so he scratched his head and he did a thought experiment. So I'm going to try to replicate his thought experiment as best I can. So what he did was he just assumed two frictionless surfaces, as you can see here, right? So frictionless surface on the left and a frictionless surface on the right. And what he did then was he kind of assumed that we have a little ball that rolls on this frictionless surface, and the ball will roll down the first one and up the other. Now, if you know a little bit of basic physics, you would possibly be able to tell me that the ball is going to roll up to the same height, right, as it is right now. And so what I can do is I'll just include a line that shows us kind of like what level the ball is at. So I'm going to draw a line here. There's a line 2. Okay. Okay. So the ball is going to be somewhat at that line, right? At that level. I'll draw that line all the way through. Okay. So now when I let the ball go, it's going to follow the curve and it's going to come up to this point at least, right? Now let's think about moving this right side surface a little bit lower. So as you can see, the ball's going to roll a little further and it will come according to the level we drew up to this point here, right? Up to that point. So if you keep moving this right side surface lower and lower, you can see that the ball is going to roll further and further along the surface, right? And let's see, let's take one more case here. Okay, so it comes up to this point, right? Now let's think about allowing this right side surface to be flat. Now you think, given that this is a frictionless surface, how far will the ball roll, right? I'm sure you'll come up with several answers to this. So if you follow the logic that that is here in terms of the ball rolling to its height, you'll realize that it never reaches that height ever. And so it will just continue rolling on forever. Now this very simple and yet unique thought experiment, because Newton didn't do this experiment in reality, he just thought it through in his mind, leads us to a statement that Newton made. And this statement is called Newton's law of motion, or specifically Newton's first law. And this stated exactly is, if a body is at rest or moving at a constant speed in a straight line, it will remain at rest or keep moving in a straight line at constant speed unless it is acted upon by a force. Now, please note, this is a law. I'll first try to indicate to you what the meaning of a law is. It's possibly it's a new word for you as far as physics is concerned. So a law is a scientific statement based on observations of how objects behave. Okay, and so coming back to the statement, we need to understand that every part of it is extremely important. You cannot leave out any of the parts there, right? And you'll see this as we go along, through the lessons, and as we reflect on Newton's first law to explain several phenomena, not just in this particular chapter, but in other chapters as well. Okay, and so let's understand what this law means. To simplify matters, this law has been also defined as the law of inertia. Okay, now what does inertia mean? If you have heard or read certain aspects of English literature or just English novels, you may have come across the word. It means a tendency to do nothing or to remain unchanged. Okay, but in physics, it has a somewhat similar meaning. That's a property of matter by which it continues in its existing state of rest or uniform motion in a straight line, unless that state is changed by an external force. Okay, so tell me, have you heard this word inertia anytime in your life. Yes. Okay, that's right. So Johnny tends to have inertia for work, which means like he doesn't really move himself on to doing certain jobs, right? So that word is used in that context. Now, inertia of motion. Okay, so let's look for that. So inertia has a general meaning in physics, but you can split it into two parts. Inertia of motion. An object in motion resists change to change. Sorry, resists change, right? In its motion. I'm sorry, the words are not complete there. Let's look at some examples for this. You may have realized that when you're in a car and you're driving along, or you're a passenger in a car, maybe at your age, you're not driving, but if the driver applies sudden brakes, what happens to you? Yes, that's correct. You lurch forward, right? Now, why does that happen? Inertia of motion, correct? Okay. So can anyone explain? Yes, that's correct. So because your body is in motion with the car, all parts of your body, and when the car comes to rest, the upper part of your body, which is not really connected to the car, is free to move forward, and so you lurch forward, right? And the reverse happens when the brakes are applied, isn't it? You tend to lurch backwards. I'm sorry, not when the brakes are applied, but when the car accelerates forward, you tend to lurch backwards for the same reason. Look at this boy down below here. He runs and jumps, but to stop is not that easy. So you tend to skid a little bit and then stop, right? Look at the third example here. You have this truck with a box on top. The truck stops suddenly, the box slides off and falls to the ground. Why does that happen? The box has nothing pushing it, or does it, right? And can anyone explain why the box falls off in front and not at the back, for example, or sides? Yes, the box is moving with the car, and so when the car stops due to inertia of motion, its resistance to change, motion, it continues to move on and therefore falls in front of the truck and not behind. So let's look next at inertia of rest. Inertia of rest is the tendency of an object to remain at rest and not change its state. So this is a simple experiment you can do at home. Take a stiff piece of card, place it on a tumbler with water inside if you like. Place a coin on top of the card. Now flick the card with your finger, or even better still, you can do this as a challenge. You ask your family members or friends, can they get the coin in the water without touching it and without actually holding the card, right? So the way to do that is to flick the card with your finger. The card moves on. The coin remains at rest because it's heavy, and later you'll see how the heaviness or mass of an object, aids its inertia, and the coin falls into the water. If you have used tools like a hammer or an axe, sometimes the metal heavy head of the hammer or axe becomes loose. To tighten it, the easiest way is to actually just take the hammer or the axe and bang the opposite end on the ground. Sorry, on the ground. In which case, you'll find the top tends to get in and get tight. It's an easy way to tighten it. Okay, this is inertia of rest. The top heavy part tends to stay where it is, but so when you're moving downwards, then it tends to just stay, and the wooden part, tends to get into the top part. Now look at this third example. When you shake a tree, the apples or fruit fall. Why do they fall? Right? Because they are heavy. Now tell me, because they're heavy, why do they fall? They don't fall normally. Why do they fall when you shake the tree? Okay, tell me, Fiona. Yes, they're held by a weak stalk. That is correct. And so when you shake the tree, the apples or fruit tend to remain where they are because they are heavy. They don't want to move. Now, that kind of motion against the stalk moving against the apple causes, it to weaken the connection with the apple, and then the apple breaks off and falls to the ground. So that's an easy way to get fruit off the tree. And now Let's look finally at when you dust a carpet, what happens? Have you ever thought about that? Can you tell me, can anyone tell me what is the reason why you can beat a carpet with an object like a stick and then have the dust come off? Or does the dust actually come off is the question. Okay, Michael, why don't you try explaining that? What do you think? So you're saying you're beating the dust off. Well, maybe, but then remember the dust is very, very tiny. It's going to be hard to beat tiny particles with that big stick. And anyway, they are distributed over their entire carpet. You'll have to beat the carpet, many hundreds of times in different places to beat the dust off. And anyway, you're beating the carpet, not the dust. See? All right, Jolyn, can you explain? You have your hand up. Yes, I think you are on a right track there. So because of inertia of rest, the dust tends to stay where it is and the carpet moves when you hit it. Got it? So the dust actually doesn't fly off. The dust stays, the carpet moves. It's the carpet flying off, the dust remaining. And that, of course, results in the dust kind of falling off, because when the dust remains, carpet moves. The dust doesn't stay there, just drifts off or blows away, And so you get the carpet clean. Okay. And so to summarize, Newton's first law, as I said, very important. I'd recommend that you learn this, verbatim. There are a few things that we'd encourage you to learn verbatim. One of these is this law. If a body is at rest or moving at a constant speed in a straight line, it will remain at rest or keep moving in a straight line at constant speed unless it is acted upon by a force. Okay. Newton's first law is also called the law of inertia, the tendency not to want to change state of rest or motion. And then there are two categories of inertia: inertia of rest and inertia of motion. Do you have any questions about anything we discussed so far? Feel free to ask me now, or you can email me or simply ask me in the next class. Right? I'm happy to answer any questions you have. But in the meantime, why don't you think about one or more examples of each, of inertia of motion and of inertia of rest? And maybe from your day-to-day life or your observations or something you've thought about regarding something that happened in the past. You may be wondering why that happened. Perhaps it has to do with inertia of rest or motion, right? So do think about one or two examples, and I'll ask you for this in the next class. All right. So thank you very much for your kind attention, and we'll end here and continue next time with a little more on Newton's first law and then going on to other laws of motion.